Just as Nicholas Copernicus introduced the heliocentric model, another stunning revision of our understanding of the cosmos could emerge, sparking a debate known as the crisis of cosmology. This crisis is marked by significant discrepancies in our measurements and understanding of the universe's fundamental properties such as its age, size, and rate of expansion. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has put an end to this debate with an image that defies physics. So what exactly is this crisis, and how does the James Webb Space Telescope contribute to it? Well, contributing to it is a bit of an exaggeration. It's more like a review that has been underway. The crisis refers to a point at which our understanding of the universe is challenged, particularly in terms of its age and size, which are linked by a considerable margin of error. The introduction of the JWST has been crucial in this context. Before this breakthrough, we were limited in how far we could see into the early universe. But with the JWST's improved capabilities, astronomers can explore much more distant galaxies, giving us new perspectives on the universe and challenging some of our previous conceptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming. These observations provide critical data that can either support or challenge our existing models of the universe. To understand the crisis in detail, it is important to review the standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter, lambda CDM model. This model has been very successful in explaining various features of the universe, from gravitational lensing to the structure of the cosmic web and the growth of galaxies. The lambda CDM model posits that the universe started with a Big Bang followed by a period of rapid inflation and has been expanding ever since. It includes components such as dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, each new observation, especially with instruments as advanced as the JWST, raises the possibility that our current model may be incomplete or in need of revision. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at different stages of the universe's history. For instance, it predicts that galaxies in the distant past should be smaller, less developed, and composed of fewer heavy elements compared to those we observe in the local universe. This is because heavier elements are formed in the cores of stars and distributed through processes like supernova explosions, which take time to occur. The description you give is about how the standard model of cosmology predicts the motions within groups and clusters of galaxies, as well as the characteristics of the cosmic microwave background, CMB, as we go back in time. According to this model, galaxies should be smaller, bluer, less developed, and less rich in heavy elements at cosmic distances greater than our own. This would lead us to expect to enter eras of the universe devoid of visible stars or galaxies. However, scientists have found contradictory evidence that challenges these predictions, resulting in a crisis in cosmology. The crisis in cosmology centers on the uncertainty about the age of the universe. Different measurement methods provide different results, leading cosmologists to struggle to reconcile these discrepancies. To address this problem, scientists use several methods to measure the age of the universe. One of these methods is the study of cosmic background radiation, which involves unraveling the history of the expansion of the universe and using mathematical models such as the Friedmann equations based on Einstein's theory of general relativity to determine the expansion rate and therefore the age of the universe at different times. The CMB, a residual radiation from the early days of the universe, is a crucial tool for this measurement. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer valuable information about the composition of the universe. However, these maps lack data on dark energy, a major component of today's universe. Despite this limitation, scientists can use Friedmann's equations along with other observations to estimate the expansion rate of the universe at different times and ultimately determine its age. The Friedmann equations describe how the universe expands, accounting for the density of different components like dark matter, dark energy, and ordinary matter. By analyzing the CMB, scientists can infer the conditions of the early universe and extrapolate the expansion history up to the present day. Another approach to determining the age of the universe involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles because they have a known intrinsic brightness. By comparing their known brightness to their observed brightness, astronomers can determine their distance and consequently the expansion rate of the universe at different times. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now central to cosmological measurements. It is especially useful for determining the Hubble constant, which is a measure of the expansion rate of the universe. Although not exactly constant, the Hubble constant is instrumental in charting the expansion of the universe since the Big Bang approximately 13.8 billion years ago. It has been observed that the cosmos has been growing steadily. NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, possibly dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it could indicate the presence and influence of dark energy, accelerating the growth of the universe. The crisis in cosmology has been further aggravated by the discoveries of the James Webb Space Telescope. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. To understand the magnitude of this scientific upheaval, let's look at the beginnings of the universe. About 150 million years after the Big Bang, stars, black holes, and star clusters began to emerge, possibly even as early as 50 to 100 million years later. However, these events should have been relatively rare. Recent JWST images reveal galaxies much more distant and therefore older than the standard cosmological model predicts. This discrepancy suggests that our model needs a significant update. JWST images show galaxies that formed much earlier than predicted by current cosmological models, triggering a crisis in the field. This problem is related to galaxies and redshift, a common measurement in cosmology. According to the standard model, hydrogen began to appear 400,000 years after the Big Bang, when protons and electrons combined, leading to hydrogen recombination. This transformed the universe into a soup of hydrogen atoms with some helium and residual background radiation. Over time, gravity acted on small perturbations in this hydrogen gas, slowly collapsing them to give rise to the first stars. However, the JWST has observed galaxies that formed much earlier than predicted by our current models, suggesting that we may need to revise our understanding of the early universe. The future of cosmology. These discoveries highlight the dynamic and ever-evolving nature of cosmological inquiry. Each new observation serves as a catalyst for deeper investigation, leading to revisions that could redefine our understanding of the cosmos. As we continue to explore the universe, the potential for groundbreaking revelations remains vast, keeping the spirit of inquiry alive in the field of cosmology. The discrepancies uncovered by the JWST and other observational tools don't just challenge our measurements of the universe's age and expansion rate, they call into question fundamental assumptions underlying modern cosmology. If our models need revision, what else might we be misunderstanding about the nature of the cosmos? One area of growing interest is the interplay between dark matter and dark energy. The lambda-CDM model assumes that dark matter is a stable, non-interacting substance that influences galaxy formation through gravity, while dark energy drives cosmic acceleration. However, what if these two forces are connected in ways we don't yet comprehend? Some researchers propose that dark energy could evolve over time, or that dark matter might have properties that subtly affect the expansion rate. Alternative theories and new frontiers. As the crisis in cosmology deepens, alternative theories to the lambda-CDM model have begun to gain traction. Some possibilities include modified gravity theories. Instead of assuming the presence of dark matter and dark energy, some scientists propose that gravity itself behaves differently on cosmic scales. Theories like modified Newtonian dynamics, MOND, and tensor vector scalar, TeVS, gravity attempt to explain galactic rotation curves and cosmic expansion without invoking invisible matter. The possibility of new particles. Some physicists suggest that our understanding of particle physics may be incomplete. Could an unknown form of matter or energy be influencing cosmic expansion? Experiments in particle physics, such as those conducted at the Large Hadron Collider, LHC, may provide clues. A multiverse hypothesis. If our universe is just one of many, then some of the anomalies in cosmic expansion and structure could arise from interactions between parallel universes. While speculative multiverse models are being explored in theoretical physics. A cyclic or bouncing universe. Some models propose that the universe undergoes cycles of expansion and contraction rather than originating from a single Big Bang event. If true, this could mean our current understanding of cosmic history is missing key phases of prior universes. The role of future observatories. While the JWST has already provided groundbreaking insights, the next generation of observatories will take cosmology even further. Upcoming missions like the Nancy Grace Roman Space Telescope, expected to launch in the late 2020s. This telescope will measure cosmic acceleration and provide new insights into dark energy. The Euclid mission, ESA, designed to map the large-scale structure of the universe and probe the nature of dark energy. The Square Kilometre Array, SKA, a massive radio telescope project that will study cosmic dawn and the first galaxies. These projects will refine our models, test new theories, and potentially resolve some of the most pressing questions in cosmology. The crisis in cosmology is both a challenge and an opportunity. Scientific revolutions often emerge when observations force a paradigm shift, much like Copernicus' heliocentric model replaced geocentric cosmology. Today, we may be on the verge of another transformative era in our understanding of the cosmos. The scientific community continues to debate, refine theories, and design new experiments. Whether the lambda-CDM model will be modified or replaced entirely remains an open question, but one thing is clear: the next few decades will likely reshape our fundamental understanding of the universe.